Hi, everyone. Hello, can you hear me? Okay. Yep, thank you. Okay, thanks for coming today. We have actually 3 more classes, just 3 more. So time flies. We are almost done. And today we're going to start the generative model. So before I start, actually, I have some announcements. In the last lecture, we covered the multimodal learning part, which was lecture 17. And I checked my schedule, and we just realized that we have just 3 more classes, and we have too many things to cover. So I kind of decided to provide one of the lecture 18, as a recorded video, which is lecture 18 is relatively shorter, and you can actually just watch it and apply the ideas we have discovered before to image and video captioning problem. So you can relatively easily follow the contents. So I already provided on ETL. You can actually click this link to watch the video anytime. You don't have to watch this before you studied today's lecture, so it's okay. You can watch that anytime before the exam. And yeah, in the remaining 3 lectures, including today, we are going to talk about generative models. And it is split into 2 parts. The first part is anything other than GAN, generative adversarial networks, and the second part will be about GAN. And the first part consists of the pixel CNN and RNN and autoencoders and its variants like variational autoencoders. And I plan to release all the lecture recordings after this lecture, actually sometime this afternoon. So if you missed some lectures before or would like to watch it again, you can actually connect this website to watch again. So any question so far? Okay, so today we will talk about generative models. But before than that, I'm going to introduce what is unsupervised learning, because this is the first unsupervised learning we are covering in this course. So far, we have mostly talked about supervised learning approaches, including self-supervised approaches. So our data is given some X, some data points, with its labels. It's sometimes it was classification, sometimes it was for regression, or sometimes it was some text descriptions of the images or videos. But we always had some labels corresponding to the data points. And our task was learning some relationship between those two, X to Y. So we approximate the function of X to Y. That is the supervised learning setting. So yeah, we have talked about image classification or video classification, some regression task, object detection task, or semantic segmentation, instance segmentations, and image and video captioning. You have to watch the video, but yeah, that's also a supervised setting. So most problems we have discovered so far is an example of supervised learning task. Now, we are going to talk about unsupervised learning. So here, we don't have any label. We are just given some data points. It can be an image or a video or some data or anything. We have just image, and we'd like to do something with that. But we don't know, as human, we know, but for computers, we don't have any labels to be given as a kind of material to learn. So for example, clustering task, probably most of you already have taken the machine learning courses. So there you probably have learned like k-means or Gaussian mixture models. So clustering is gathering similar or relevant examples together. And if examples that are not similar to each other, far away. So the difference between this one and the metric learning we have covered, where that's the goal looks like similar, but in metric learning we use some labels. But here it's we don't have anything. Just we have to use just the image itself or the video itself. So clustering or dimension reduction or density estimations, these are the most popular and important unsupervised learning task. But we are not going to cover these things in this lecture. So we will learn more about generative models, which is this. Given the training data, which is just X, only the images, assuming there is some probability distribution which has generated those data. So we usually express this like only the gods know this distribution. We don't know. We just collect some samples of the images. And we assume that there is some distribution governs existence of these data points. So using those samples, we would like to estimate what that governing distribution should be. So we call this as a PX, and we are going to use our model to model that distribution. So we can either explicitly estimate those density, so we actually have this PX in hands, or we sometimes just want to not actually need to estimate those densities explicitly, but we just want to sample other images, other plausible images from that distribution, even though we don't have any mathematical formula to describe that distribution. So why do we want to do this? So we have some examples like this, and then we learn some density which governs production of these images by the nature. And we would like to sample some other plausible images out of that. So that is the goal of generative modeling. And yeah, why do we do this? Well, there are a lot of different goals or motivations of doing this. One is realistic samples from training data. So we have some finite number of data points in hand usually. And if we are able to generate some plausible images, then they can be used in many ways for some, I don't know, for other applications outside of machine learning, but also we can use those as a training example. There are a lot of possibility that we can take advantage of those fake samples. Or we also would like to improve our models. We would like to improve the quality of the data, like super resolution, which we are going to cover today. Given some low resolution image, like 32 by 32 or 100 by 100, very small images, we would like to increase its resolution to make it more clear. Or given some black and white images, we would like to colorize photos taken like 100 years ago. Everything was black and white. Now we can use our recent technologies to color them, which is great. So yeah, these are some important applications. Or we can also use the generative models to learn some useful features for downstream tasks like classifications. Or we can also get some insights from high-dimensional data. Especially these are important for scientific applications like physics or medical imaging. Though in those areas, it's less important to, it's important, still important, but it's not the end of the world, just making the state-of-the-art results. In real applications of information technology services like web search or recommendations, we always just want to make it as accurate as possible. And that's it. We just want to have some more revenues or, yeah, just precision and recall. All those things are just important things. But in physics or medical imaging, we actually not only want to just improve the performance, but also we would like to be able to interpret it or why that's happening. So that's another thing that we can use generative models to get some insights here. So yeah, generative models have a lot of motivations like this. And yeah, we're going to see one by one today. So yeah, I took this image from Ian Goodfellow's tutorial, which was published in 2017. Especially if you are interested in generative models, this is a really good text to read. So generative models are divided into two groups, with explicit density modeled or implicit density models, which we don't actually have the mathematical representation of the px, but we can still generate examples. And then below it, explicit density models are split into tractable density versus approximate density. So sometimes the density can be really simple, so we can tractably solve it, or sometimes it's too complex and we cannot model as it is, so we use some approximate method. And in direct density, some direct ways or stochastic ways. So I'm not going to explain all the differences between these things, but today we are going to cover pixel RNN and pixel CNN, which is the tractable density model. And we're going to see very briefly about the autoencoders, which is really simple models. And then variation autoencoder is quite well relevant to that, but it's not just a simple extension of it. So lecture 19, we'll be covering about these two. And in the next lecture, lecture 20, we are going to see generative adversarial networks, which is a huge topic, actually. In some schools like Stanford, they have a semester-long course only on this generative adversarial networks. So we are going to just very briefly see the most important papers there and just give you the basic ideas. But if you're interested in this, then maybe you can actually study a lot of relevant papers in this topic, indeed. And this lecture 20 is relatively longer because I have too many things to cover, but I didn't split it into multiple lectures. But in the next 3 days, including today, we are going to cover these 2 lectures. Sounds good? Okay, let's talk about the first method, which is pixel RNN and pixel CNN. So we are going to generate an image. So far, we were given an image, and our task was figuring out what it is. Now, we would like to generate some image which looks plausible to human. So it's completely different task. So how the machine knows whether this image is plausible or it's image-like to humans. So that should be learned from a collection of the data sets or images. And we kind of teach the machine that this is plausible image, this is plausible image, this is plausible image. And it needs to figure out what is the pattern inside that. And then it needs to draw something plausible to human. So as I said, we assume that some probability distribution exists. We don't know what it is. Only the God knows. But we have to estimate that based on our samples in hand. And then we can use those P probability distribution to generate other images. And here we assume, in this method, we assume that there is some order of pixels to generate. It can be any arbitrary order, like this, from row to row and column to column, like this. Or we can do diagonally like this. Or we can jump with some stride like this. Any order is fine, but we are going to generate the image in some order, which is predefined. That is the assumption of this model. So something like this. The task of this model is, given a partially generated image according to this order, and I'm going to assume we are using this order, but any other order is still fine. We are given this image, which is partially generated, and the task is the very next pixel to be generated, which is this one. So we would like to learn and estimate the probability distribution of the next pixel. And here we assume RGB codes for each pixel. So we need to estimate the probability distribution over 0 to 255 for each R, G, and B channels. So this is an example. So given this, the model estimated that the red will be distributed like this. So most likely it's like 128 or somewhere like that. Green looks like that. Blue looks like that. So we can sample each value from this distribution, and then the color will be decided. So here, starting from the empty image, at the very beginning, we don't have anything, right? So just given the empty image, it iteratively generates pixel one by one. So in the given first image, which is nothing, then it estimates the probability given that image for the first pixel. And then we will get this distribution. And to make this as a stochastic process, we don't decide the pixel deterministically. Actually, we just sample from this distribution. So this blue, for example, means this distribution means that it's highly likely the value is around 50, but it's not deterministically be 50. We just sample according to this this distribution. Then it's likely to be 50, but it can be still like 200 with lower probability. So in that way, we sample the first image, and then first pixel, and then given that pixel, the second pixel will be estimated with this probability again, and then we're going to sample the second pixel, and we just repeat that process until we have the entire image. Okay. So mathematically, we can write this approach like this. We have learned about chain rule, right? So we can actually apply this chain rule to write about this. So I'd like to write some mathematical formula, but I'm going to just explain in words. Hope you can understand it. So I is equal to 1 to n squared, which means we have n squared sized image. And for the very first one, I is equal to 1. And x1 to x0, so actually nothing. So the very first one is px1. So the first pixel is just sampled from nothing because we don't have anything yet. And the second pixel, which is probability of x2, is x1 to x1, so it's just x1. So we multiply px1 times px2 given x1, and px3 given x1 and x2. And then px4 given x1, x2, x3. And that is repeated until we have p of xn squared given all the rest of the pixels. That is mathematical representation of what I just discussed here. Okay, so this is abstract representation, but it's exactly the same as what I just mentioned in the previous slide. And because we have 3 channels inside each pixels, actually we also sequentially generate each of those channels. And here, similar to the order of pixels, we also need to define the order of these channels. And just for convenience, we use that order, RGB. So probability of some particular pixel given all the previous pixels is multiplication of these 3 things. The first one is what would be the red color components of this new pixel given all the previous pixels. And then because we already generate this red one, that is given as a condition here. So all the previous pixels and the red color is given. Then what would be the green components of this pixel? And then here, both R and G are given, and all the previous pixels are also given. Then what would be the blue color of this pixel? So we generate in that order. And then we move on to the next I, which is I plus 1, the next pixel, given all the previous pixels. We just repeat this. As you can imagine, this is extremely slow because we have to estimate the probability for each of these pixels, and we have to sample them, and we have to repeat for all the n squared times 3 numbers. So yeah, that's unavoidable. It's sequentially generating the entire image, so it's just super, super slow. So they presented 3 specific approaches, 2 using RNN, 1 using CNN. So we are going to see the actual method of doing that. The first one is the RNN setting. So yeah, the input is given as just empty image. It's not generated yet. And we start with some initial hidden state, just randomly initialized. This is RNN. And then how our RNN was working. We take this input and previous hidden states, updates them using some formula. We're going to see that again. To update the hidden states to the new states. And it outputs whatever we want, which is, in this case, the distribution of the RGB channels. So for the first pixel, so given nothing, we are going to generate the first pixel at the first step. And this first hidden state outputs the distribution for the red, green, and blue. And from there, we sample one value to fill this. And the loss is computed by comparing against the ground truth image that we're going to generate. And this will be the difference between these two in the first pixel will be given as a loss, and it will be backpropagated to the model. Then, now we have generated the first pixel. So now we are able to see the first pixel's value, but not the generated value, but we are using the teacher forcing, because at training, we are given the ground truth value, and then what will be the next pixel? The model needs to learn that. At inference later, we don't have access to the actual image, so they have no choice but to use the values they have generated. But at training, we have to use the ground truth to actually force to make this same image. So the input is given like this. Only the first pixel is available. Updates the hidden states as regular RNNs. And output the distribution for the second pixel. And we sample the second pixel here. And again, the distribution, the loss between these ground truth and the generated value, actually the distribution, our estimation for that ground truth, because they are using cross entropy. Anyway, the loss is computed between these two, backpropagates to the model. And that's just continuing to be repeated. So given the 2 pixels, they generate the third pixel. Given the 3 pixels, then generate the fourth pixel. So it's naturally fit into the RNN setting, right? So they apply these RNN models to generate each pixel one by one. Actually, in R and G and B are also generated sequentially, but I didn't draw it in that way, just for convenience here. So yeah, you may remember that this is the RNN formula. Actually, it's a LSTM formula. So whenever we say RNN here, we are going to actually use LSTM, because that we know that we have covered that, why we have to use LSTM or GRU. So they applied actually the LSTM. So we have these components to learn. And this is the formula of the LSTMs or RNNs. Given the previous hidden states and the input values, they are multiplied with some linear weights, the trainable weights, and then goes through some sigmoid function to generate the next hidden states and the output out of that. So I didn't write all the formulas for that, but this is how we update the hidden states. And here they used actually convolution instead of fully connected here, W and U. So this is more like actually conv LSTM, not just LSTM, because they use convolution here. Please review lecture 13 or 14 if you're not familiar with this. We have already talked about that. So they call this as row LSTM. So they generate the hidden states from each row, from hidden states of the previous row and image of the current row. So let's see, what does that mean? Suppose we have generated the first 2 rows already. And then our goal is generating this the first pixel of the third row. And then where they actually look at. So again, because this is RNN, there are 2 inputs. One is X, the input, and the other is the hidden states, the current hidden states, right? So the current hidden states is HT-1, and it's convolved with U. So that is this part. So here the previous means in this model, that is the previous row. They generate row by row, and at this time step is 3, they use the generated row from the second row. So for this one, they use these 3 values, where this will be 0 padded. And then the input, which is xt, that is actually this input image. It learns to generate from this. So the actual pixel location and its window size 3. So this part is actually used and convolved with W here to figure out this part. And that is repeated like this. So for each position, they move the window like that to model the relationship between these pixels and these hidden states by using U and W. Just same as RNN, but just they would like to figure out what these hidden states should be here. So one thing to notice is that this process is actually done in parallel, not sequentially, because the entire row is given. That was done previously, and this entire input image is also given. So we can compute each pixel in the same row at the same time in parallel. So that actually expedites this process. Okay, so then let's analyze how it actually works and what's the potential problem of this. So hidden states of this model, taking the information from that input image, we for this one, when we generate, when we fill in this part, what we use are the 3 corresponding previous rows pixels, the channel values from the previous row, which is these 3. So this one is determined by these 3. And then what about this one? This one is determined by these 3. And this one is determined by these 3. And the last one is from these 3. Which means this pixel is determined by this trigonal-shaped region of the image, not the entire image. Do you see that? Because this is too small image, but suppose we have much more number of pixels, and given some points, then it refers to 3 pixels right above that, and then 5 pixels right above that, 7 pixels right above that. In that way, it will actually look at only the triangular-shaped region within the entire image to learn what it should be. So it cannot actually look at the entire image. It means it has some blind spots, like your car. So receptive field is triangular, not covering the entire pixels previously generated. So this is not great. I mean, we should be able to take advantage of the context in the entire image, but this model actually loses that. So what they tried is another type of LSTM model. So interestingly, this slide is exactly the same as before. You see, because this is LSTM, the RNN, the formula is exactly the same. LSTM formula is still exactly the same. The only difference is that what are these H and X are assigned. So that will be just the difference. But now they try to apply by LSTM in a diagonal form. So let's see how they do that. So again, they take the actual input, xt, and previous hidden states, which means the hidden states of the previously generated pixels, and the value for a particular pixel will be determined based on those 2 by convolving with the linear weights like W and U. So from this, for this particular pixel, they actually generate diagonally. So at the very first, they generate this one, and then these 2, and then these 3, and then these 4, in that way. So diagonally, starting from the left top corner to diagonally generate until the right bottom. So for this one, for example, they refer to the pixel right above it and the pixel right left to it. So these 2 are considered as its previous hidden states for that part, for that particular pixel. So those two are the ht minus 1, and xt is the actual pixel corresponding to that region. So that is the only difference. Once you choose the xt and ht minus 1 correspondingly, then that model will become like this diagonal by LSTM. If you choose those areas like this, then that will be the raw LSTM. But the formula, this is exactly the same. Just the difference is what you are giving as an xt and as a ht minus 1. So if you do this, then one good thing is that actually it can refer to all the areas which is already generated. Is it true? It's almost true, almost better than before. It actually refers to all the pixels to the left and to the top. So it misses some areas here, but that's still so it's still better than before, but it's not complete. So what they did is where it is actually. I wrote that somewhere. They repeat this. Here repeats this in two directions. So starting from the left top to the right bottom once, and then right top to the left bottom, and they repeat this alternatively. So then they're going to take advantage of the previously generated pixels from the left and the top once, and the right and the top once. So where actually they can do that in 4 corners. I don't know why they didn't. Probably that should be okay, because in the very last pixel, for example, the right bottom, that actually takes advantage of the entire image, which is already generated, and the other way is also around. So that's what they did, and because they use only one pixel here from the input to state, so that they use the 1x1 conv, and this one, the state to state is 2x1 conv, because the input is just 2 cells here. So for easier implementation, they did some trick, which is called I don't know. Probably they didn't name it. So they use some tricks to skew the hidden states. So this is logically what they do. To learn about this part, they refer to the right above and the right left, like this. But because these two are not consecutive, then it's harder to code or parallelize them. So they skew the image like this. The first row is 1, 2, 3, 4. Then the next one is 2, 3, 4, 5. They skew each row like that, and then each pixel is determined based on the right, left, and above it. So they use these two as their previous hidden states to determine the next pixel. So it's just implementation details, and you can refer to the paper for more details about this. But in that way, actually, the receptive field is global, which means they use all the pixels that are generated so far. Because this one is determined by these two, this one is determined by these two, this one by these two, and this one by these two, this one by these two, this one by these two, in that way. Okay? By the way, this paper is really, really hard to follow, unfortunately. I tried to understand all the details of these papers, and I really had a hard time. This is not a good paper to read, actually. But they have very brilliant ideas, and it was quite impactful. But the way they write, I really didn't like it. Anyway, you guys may also suffer from that. Sorry about that. So their third approach is called Pixel CNN. So originally I thought that this is a newer version of their method, but actually all these three were in the same paper, interestingly. So instead of using RNNs, which is still they generate sequentially, but instead of using RNNs, the model consists of stacked convolution layers. So it's basically the CNN with very weird shaped filter like this, because they generate row by row, and in the same row they generate from the left to right. Given 3 by 3 corner like this, given this center, all the rows above that and left in the same in the center row, these 4 are previously generated, which is known. The other 4 is not known. So suppose we apply the convolution here, this gray area is known, so we can use those values when we learn the pattern. But the other white area is not generated yet, so we should not refer to that area. 5 by 5 looks like this. So basically, they use this shaped convolution layers to learn the patterns and to make the to determine the pixel to generate at that point. So given the context within these shaped, and they are actually stacked, given those shapes, they learn the patterns, then they decide to what this new pixel should be. And then they repeat to the next position and again, right? So in implementation, the training can be done in parallel, again, because the input image is the training data is given. We are not generating, well, we are generating them, but we can still use the training data. So all of these values are actually known, but we have to pretend as if not, because the model needs to be able to generate this pixel only based on this area, not using this, even if that's available. But because of that, we can actually do this in parallel. For any given location, we can just use the allowed areas only based on this shape, and we can just hide the others. So as the training image is given, we can always run this in parallel when we train the model, which is great, because the RNN-based model, that's not possible. We have to generate row by row or diagonally in that order. But in CNNs, actually, we can generate all the pixels at the same time, only in training. In evaluation, we don't have any access to the entire image at the beginning. We have to generate one by one. So at inference, it's still slow, but training is much faster. So yeah, this part was really hard for me to understand, but now yeah, I'll try to explain it. So they use 2 types of mask type A and mask type B. Mask type A means when we generate R, we can access only the context. Here, the context means the previously generated pixels, which means when we generate this part, the red color of this pixel, we are allowed to refer to only these blue pixels, the previously generated area only. And when we generate G, then we can use these blues and also the red components of this target pixel. So G refers to R and the context. When we generate B, what we have so far, we have the context, the blue, and R and G. So mask A uses only the information that we already generated, the previous pixels and the same pixel which is preceding to that particular color code. Okay? Mask type B is slightly relaxed restrictions. When we generate R, we are allowed to actually look at the context, the previous pixels, and the same component as well. We are not still able to see the future, but they actually look at the red components of the same pixel. Why? That's weird, right? So that's why actually they have mask and B, A and B, 2 types. Mask A makes more sense at the very first layer where we actually consume the actual image. So when we actually have access to pixels directly in the input image, we must not actually look at what that value was. Otherwise, we are not going to learn anything. So when we estimate the probability distribution of the R, red color components of this pixel, what's the information given? The previous pixels, the context. Given these, we try to figure out what should be the red component of this pixel. So at that point, we should not access the red components of this pixel, because that's the right answer already. So to make the model actually learn the relationship, we should not use that. But after that, once the first layer is done, then the second layer does not directly access the very input image. It actually accesses only to the previous layer, which is the first layer, which is our estimation. Right? Do you follow that part? Because this is a multi-layered model, at the very first layer, we directly consume the image. So we have to avoid actually looking at the right value for each pixel. But after that, after the first layer, the second layer actually look at only the first layer's value, which is our estimation. So there, they use this mask type B, which is they refer to the context values and the same components values of that particular points, because that's our estimation. Still, it's allowed, but it still cannot be look at the future pixels or future color components. So that's why they have both these types of masks. And mask A is used at the very first layer only, and after that they use the value they have created for that particular pixel and its time the color components. Other than that, actually, you can follow the paper to figure out what's their actual model architecture. So all of these three are actually proposed by one paper. And you see that they start with 7x7 conv with this shaped mask A. And then it divides into three different models. So in raw LSTM, input to state was 3x1. Do you remember that, the window thing? Using the mask B, and state to state was also 3x1. And there they didn't use the mask because it's from state to state, not from the input pixels. And diagonal by LSTM, it was like input to state was just 1x1, just one pixel. And then state to state was the 2 pixels. One is above, one is the left. So that's why they have 1x2 convolution here. And pixel CNN, they use 3x3 types mask B, which looks like this. And here the yellow means they refer to the context as well as the same or the previously generated color components. And then followed by 1x1 conv of type mask B. After that is the same, just softmax to generate the probability distribution of each color component. Okay, so I know it's really hard. This part is not easy to follow. And unfortunately, the paper is not easy to follow as well. But please take your time to review this material if you are not, if you didn't understand the most components. And also, please read the paper many times to try to figure out what's happening. Especially this table summarizes all the model details, but to understand what's exactly happening, you may have to spend some time. All right. Now we are going to use this model to super resolution task. So this is a new task actually in this course. So the task is like this: you are given some low resolution image like that, and your task is generating high resolution image, which is plausible to this low resolution image. So this is the ground truth, and this is the 8x8 downsampled version of this ground truth. And then your task is generating some image which makes sense to this low resolution image. Interestingly, where they look definitely a different person, but still it's surprising because just by looking at this 8x8 image, can you imagine that this is a woman or man? I even can't see that, but actually this model was interestingly generate quite similar looking faces. So this is from 2017. So it's like 4 years ago, but they were able to do this at least in this quality. So yeah, let's see about this task. This task is underspecified. What does that mean? Given this image, there are many plausible high-resolution images. There's no just only single answer. There can be multiple answers, and all of them can be plausible. So we need to guide which one that should be from our data set. So it needs to consider texture, edges, or viewpoints, illuminations, occlusions, and yeah, it explains all the difficulties they encounter, even though they don't resolve all of them with this single model. So yeah, it just basically says that this is a hard problem, and basically just generative model doesn't have the right answer, unlike the classification. So that is the hardest point of this generative model, because they need to think about how to evaluate. So for example, given some generation of this image, then how can you quantize how much this is good or not, like loss functions? So that's hard to define in this setting. So generative models are basically challenging because of that. And here I summarize the notations they have used, because these notations are not quite standard. So X denotes the low resolution input image, this 8x8 image. And we say that that has L pixels, standing for low. And Y is the high resolution predicted image. In machine learning, usually we use Y hat for the generated, but they use just Y for the predicted image. So don't be confused. And Y hat denotes the ground truth image. In machine learning, they use just Y for this, but they use Y hat. So sorry, Y star. So you have to be cautious about this notation. So that's why I wrote it here. So let's see how they apply the pixel CNN models to do this super resolution. Actually, that's quite simple. So the task is the model is given some image, partially generated image like this, just as the pixel CNN setting. Just partially generated image is given. And the task is estimating the probability distribution for the next pixel, which is called pixel I here. And then they run the pixel CNN, which is called prior network, to generate these logits. So it's just applying the pixel CNN. That's exactly what we just covered. So given this image, given these partially generated pixels, what it should be. As a human, we can say that that is part of face. So it will be some skin color of this person. So we can, as a human, we can actually say that. And that means this machine learning model will be also able to capture that kind of patterns from the data. So they use pixel CNN models to learn the distribution of this part. So this model maps from high resolution image generated so far to probability distribution over all the possible values for RGB for the next pixel, the pixel I. And this one captures the sequential dependency of these pixels, which means they use the previously generated pixels to determine the next pixel, as the general pixel CNN model does. So far, so good, right? Then, what are missing? We're now solving super resolution, not just generating some face that looks plausible, but it should be matching to this low resolution image. Okay? For that part, they use another CNN, but this is given as an input, so they don't have to hide anything. Use this entire image and apply some just regular CNN models to generate what this pixel should be. So as a human, again, we are also able to use this information to estimate this, because we know that this corresponds to somewhere here, and we see some general patterns. So yeah, it's actually possible that this lady may be holding some something like some phones with red color. Then suddenly this can be read. And that should be shown here somehow. So we have to use that information to generate this image. So this conditioner networks also outputs the same thing, the logit values for each of these color distribution by mapping the entire low resolution image to this particular pixels distribution. And this one captures the global structure of the input, low resolution image input. And they sum both of them and then take the softmax to finalize the score distribution for the RGB. And then from this, they sample the next pixel and move on to the next one, and just repeat all the location of the pixels to generate. So they, to summarize, they actually just use the pixel CNN, but they also added the conditional network to take into account the input low resolution image to condition the output. Okay, so let's see how it actually works with some more details. Looks complicated, but it's not. So yeah, this paper is well written compared to the previous one. So the output of this model gives the probability distribution over all possible values for each target pixel. So probability of the next pixel given the previously generated pixels and the input low resolution image, right? This X is low resolution image, Y is the predicted image so far before I. And that is based on the softmax of model A, which is this part, conditioning network, taking X as input, and plus BY, which is this part, prior networks B, using Y less than I. So it's determined by that, right? And using the definition of softmax, we can write as this. And this part, exponential of these two scores, means the distribution of the scores for each possible values, 256 values of the pixel color intensities. So this part is the vector of size k, which is 256, and it's divided by some scalar values, which is the normalizer. And this is the loss function they use, which is the cross entropy. So recall that this is the definition of the cross entropy, right? The actual value multiplied by log of our estimation, right? That's the definition, minus of that. That's the cross entropy. So here, this Y is a vector of 256. And in the ground truth, only one of them will be actually 1 from the actual pixel value, intensity value from the actual image, input image, the ground truth image, right? So that's why we are using the one-hot encoding here. So that part will be tricky to understand. The Y hat is changed to this notation because it is each pixel is actually represented as a vector of size 256, one-hot encoding. Only one of those values are 1 and all others are zeros. And our estimation is also in the same size. That's why I mentioned this. Our estimation is also a vector of size k. And we have the probability estimation for each of those possible values, just like this. For one distribution, we have some values corresponding to each possible values, and that is this one. So these two are taking the inner products, which means I said only one of these values in the ground truth are 1, and all others are 0. So only one value within this will be surviving, which corresponds to the actual values, our prediction for that actual intensity. Are you following that? All right. So, and then this is just a mathematical substitution. So this part is substituted with this one. And then in the paper, equation 7, it just says that it doesn't show all of these things and just says that this is our result or our loss function or something. And we covered all of these to just help you. So it looks like this. So you can actually follow from here. So using the property of the log, you can actually do this. This one multiplied by log and the above minus 1 y transpose log and the denominator, right? So this part is the same. The log and exponential are canceled. So only this part transposed this part. So that is the left part. And the right part, it's tricky. It says LSE, and what does that mean? It's log sum exponential. So this part is here, and then log sum exponential and the rest. So that's their tricky, weird notation. But I kind of recovered all of these things for to help you to understand the formula. But basically, that's exactly what they do. Only using this simple formula to estimate the probability distribution and apply the cross entropy to optimize it. And that's it. So this is the result. Because this is a stochastic process, I mentioned that each pixel is not deterministically determined. It's stochastically sampled from each estimated probability distribution. Every time you run the model, the inference, then the different, slightly different results are created. So for this image, they created these 4 faces, and for this one, this 4. They look similar, but quite different. So that's why I would like to show that this is a stochastic process. So yeah, that's it. So we have talked about the super resolution using pixel RNN and pixel CNN models. Again, I know this is not easy to follow. Please read the paper carefully to try to understand what's happening inside of those models. And autoencoders. Okay, so yeah, we have enough time to do this. Autoencoders are easier, much easier than before. So just relax. This is another unsupervised approach for learning a low-dimensional feature representation for some data points. So this is actually a brilliant idea. We don't have any labels, but we still would like to figure out what's the contents of that image or anything, like video or anything. So what they proposed is we build some encoder models to reduce the dimensionality of the input to some small dimensions. Like the image is supposed like 3072, but this Z is just 100 dimensional. We encode some useful information to that, and then we have another decoder model to map it back to original input. And the only loss they give is the input and output should be the same. That means the model is allowed to use only, suppose, 100 values to represent this entire image. And it needs to learn what is the most important signal from that image to recover it back from that small number of information allowed. Okay? So trained only with this reconstruction loss. So the one great thing with this is this can be applied to any kind of data set, not just images, but sounds or videos or, I don't know, anything, any measurements, scientific measurements, anything. You can actually just apply very long vectors here and then map it to small vector called Z, and then recover it from that. That's it. So the main purpose of this is representation learning. So this decoder part is actually not used. This part is only used during the training to map this back to the original value, and then we have to compare that. So decoder is used only during the training, and then once it's done, we assume that this encoder actually learned the patterns, general patterns of the image, because they have to share this encoder for all the input images. So they need to figure out what's the general pattern shown in this image, not each image is specific. So they learn this encoder, and then given a new image, then we can use this encoder as a feature extractor. So that this one is widely used for that purpose. So we can do some embedding, manifold learning, or feature extraction. These terms are just indicating the same thing, basically the same thing. And yeah, that's all everything I already mentioned. So yeah, we can say that we temporarily attach this decoder to this encoder model to train this. There is a reason that I mentioned this, because we are going to see the opposite case in the later models. Okay. So that's it for the autoencoders. But some people try to slightly improve the autoencoders a little bit by adding random noise, similar to data augmentation. So because the image, as we know, all the pixel values are quite stochastic, which means if we take two shots in a row, the pixel exact values were slightly different, even though it captures exactly the same scene as we perceive. So they try to add some random noise to the image, but still that semantics of those images doesn't change. It's like the image augmentation. So noise examples like this, zeroing out some random pixels, which means we are just adding some black dots, just like the old films. And we can sometimes add some Gaussian noise to the pixel values intensities, or sort and paper noise. So randomly add some white dots or black dots to the image. Still, as a human, we can perceive what that image means. And we also want this model to learn that as well, regardless of those small images. Why does that work? This picture is from the paper to explain that. Suppose this black line represents just semantically means that this is where each image can be anywhere in this two-dimensional space, but only on this black line, we human perceive that as a plausible image. So if that image goes far from this black line, that means still it's two-dimensional matrix with some color pixels, but as a human, we believe that that's not a plausible image. So all the data points observed, X here, means they lies on this black line. But if we add some noises like salt and pepper noises, then it will move these data points slightly farther from this black line. So input data X lies on closely to this manifold. And some corruption actually moves this to some other points far away from this. And then our model learns how to map this back to this image, because we are going to compare against the actual image, not the corrupted image. When once this model encodes and then decodes back, then it will be compared against the actual image. So this model learns how to map it back to more plausible image space. That's how they interpret why this one is actually useful in the paper. So it's kind of interesting idea. Well, autoencoder is simple. Just build some encoder and decoder and use some small bottleneck layer and just give the image, and then we recover it and then take the scared loss to compare them, and that's it. Boom. So it's really simple, but there are some limitations as well. So let's see that. Autoencoders are mainly used to embed the input X to a learned manifold space. So basically, this is learning representation. How can we represent an image in a compact space without losing information as much as possible? That's the representation learning, right? So that's done. That's well done. Actually, that's working nicely. But now, we have used this decoder to train this autoencoder. Can we reuse this generator to actually generate some new image, right? So that idea actually failed. We originally thought is giving some Z, then it will generate some plausible image, but actually that's not. So we need the original image to get this Z, but without that, actually, we don't have access to this Z vector. There's no way to get it. So it's not possible to generate from this Z to some plausible image X. So well, directly using this decoder doesn't make sense. It's only working for the vectors generated from the actual images. That's not what we want. We'd like to generate some new image. But still, it's probably working. It's still, there should be some way to make it happen, because this actually reminds our definition of the generative model, which are given the actual images, X, and we encode them into some our probability distribution model, which is Z. And then using that, we should be able to sample from that distribution. So why does that is hard? We should be able to do somehow. That's the motivation of this variational autoencoders. So what we want with a generative model is there should be some plausible images in some distribution. It's called PZ. And we'd like to learn some generator, which is called G, to have this image. So something like this, as a simple example, we have just images of 4s and 9s, handwritten images like MNIST. We'd like to learn some distribution, generating these data images. And it will looks like this, for example. And we can interpret that this is for the 4s and this is for the 9s. And if we sample some image from this distribution, we're going to get some image looks like 4. This part, we're going to get some images like 9, right? So is there any way we can do this? So we'd like to estimate the probability distribution of Z like that and sample from it, which looks semantically reasonable image to each distribution, each mode of those distributions. So how can you achieve that? The very first try was like this. Suppose a set of images are generated from some latent distribution Z, which is our assumption, which means our distribution is integration over all the possible Z's, all the possible latent vectors of our generator. But that's not possible, right? We cannot count all the possible Z vectors. So we have only some finite number of samples. So it is approximated as a sum of those samples. That's usually what we do with machine learning, right? So instead of integration, we have summation over all the images we have. And that is, given this Z vector, we use our generator and estimate the probability of each image in the data set. And that is summed over all the distribution of Z. And that is actually the definition of expectation of the probability that we would like to measure. So, okay, we as we do for all other machine learning models, they tried maximum likelihood models. So likelihood function, you recall that this is the likelihood function of all the data points I. So each data point, we have n data points or n images. And for each of those zi's, we feed it to our generator. And we estimate the probability of this actual image. And we would like to train this generator such that actual images have the high likelihood values. That's the idea of the maximum likelihood, right? So just apply that idea. And just mathematically, it's just automatically done. So we likelihood function, then we take the log likelihood. I'm not going to repeat all of these basics. So log likelihood function, and it looks like this. So from there, let's assume that our model follows the Gaussian distribution. This is just our assumption. It can be any distribution, but to just make it easier, we assume that we have the Gaussian distribution here. And then our log likelihood function will look like this, using the definition of the Gaussian function into this P, and it will look like this. Okay. And then we take the above will be like this, only this part survives. And the rest of them is not relevant to this mu and sigma, so they're just noted as constant. This is the log likelihood function. And then we would like to maximize this. Then how do we do that? Just taking the derivative of this log likelihood function with regards to the parameters, which is the mu and sigma squares, to get the maximum likelihood estimation. And that actually shows that it looks like this. Let's interpret this. For each examples, we sum these things. And what does that? It's distance between the actual data points and the images that our model generated, output of our generator. So that means we have to generate our models as much as similar to the actual images, which is right. That's what we would like to do in terms of squared loss, right? Is it the right thing to do? The question, is the squared loss a good indicator of image semantics? In other words, if our generated image is similar to the images we actually observe in the data set, in terms of squared loss, then does it preserve the semantics of those images? No, right? We have seen some examples like that before. This one actually shows that the square distance is not a good indicator of the semantics of the images. So this trial actually failed. They tried to generate the images under this assumption. Okay, let's assume our distribution is the Gaussian, and let's try to do the maximum likelihood as we do for a lot of machine learning models. And then, boom, it turns out to be just minimizing the squared loss, and it actually does not convey the semantics of the image. Okay, so it's failed. What should we do? So this is the main idea of the variational autoencoder, which is actually not very different from the previous idea, but we're going to give some additional conditions to preserve the semantics. So here's the thing. Instead of, we sample Z from PZ given X, which semantically distinguishes image observed in X. So instead of this Z can be anything without any restrictions, that failed. But now we kind of given the condition that this one have to follow the distribution of Z given X, the images, the data sets. And because we don't know what this is in nature, we use some other distribution which can be approximated to this P, which is called Q. And this one we actually define its form, parametric form, and we can actually optimize over them. But there we are going to use some idea from variational inference. But I think most of you may not be familiar with what it is, and so am I. I just know it's high-level idea from when my old study at graduate school. So I'm not going to go to the details of that, but just know that, keep in mind that we're going to use some surrogate distribution, which is called Q, and we are going to optimize that. And we are going to have an additional condition that this one should fall similar to the P we are going to match. So this is the summary of this model. In the first try, PZ can be anything. And we hope that we can just slightly change the value of the Z to get some plausible images, but that actually failed. So now we are going to explicitly force the PZ to reflect the observed examples, which is PZ given Z given X here. And then we assume the form of Q, same as P, for parametric optimization. So we're going to have some complex derivations. I'm not sure if we have enough time for that. Let's see. We have, 6 more slides. We may stop here. Let's see. Let's just finish the slides, only the slides. So here's the derivation. So given log px, we multiply some constant, 1, because this is some distribution over z, but we are taking the integration over z. This is exactly 1. And because this log px is a constant in terms of z, it is moved to the inside, right? Then we apply Bayes' rule, which is this. You guys should be familiar with this, to this. Px is written as this. Okay. Then I apply some colors here. Before then that 1 is multiplied, which is q divided by q, the same thing. And that is multiplied inside of this. And I apply these colors here. And I'm going to use these colors to distribute into 3 terms using the characteristics of the log, just organized by color. Okay. And then the first one is the definition of the expectation over this probability distribution. So it's an expectation of log px given z. And the rest of 2 are actually following the definition of the KL divergence, which is this. Probably we have seen this in lecture 3, a long time ago. So this is some kind of distance metric between 2 distributions, P and Q. So actually, these are KL divergence between these 2 distributions. And this is likelihood. So we'd like to maximize this, right? What does this mean? Given z, the probability of x, and we would like to maximize it. What that means. Given some vector z, the probability of the actual images x should be high. That means this is the reconstruction of the data set. So to make this part larger, that means our model should output some images looks like the actual images in the data set. And this part is actually what we had before in the failed models. But that failed because we didn't have the rest. If we just follow this, then that will fail. It will just optimize the squared loss between the images, but that's not enough. So what's the second part? QZ should be similar to PZ because this is minus. We have to minimize this. So that means we have to force that the encoder Q embeds the data X to a prior distribution of PZ, which we assume as Gaussian. But any form is fine. We are using some Gaussian form for our Q. Recall that we are adopting this Q because we don't know PZ given X. So we just use our some preferred form, which is Gaussian. And we would like to make it similar to PZ. Without this, without enforcing this, actually that will fail as the previous one. And the last term, we actually can't do anything with this because we don't directly work with the PZ given X. We are only working with Q. So PZ given X is, we don't know that. So this part is uncontrollable, unfortunately. But we know that the KL divergence is always larger than 0. So this part is some constant, positive constants. And we have nothing to do with that, but we just know that that's kind of making it a lower bound of this log px. So yeah, we are going to finish here today, and we have some few more slides for variation autoencoders. We're going to just review this and finish this in the next lecture, and then we're going to start the generative adversarial networks again. Okay, thanks for attending, and if you have any questions, I will have 10 more minutes to answer.